All right, so let's do one like this. So let's say we have a wall and a pin joint at the wall and a rigid body here, and then I'm going to make a little more room. What? No, this is the next stuff. This is statically indeterminate systems. And then let's say there's a cable here and a cable here connected to the ceiling. We're going to assume that this thing is rigid. Those cables, because they're a lot thinner, a lot less material, are going to deform a lot more than that body is. Okay, so this thing's rigid. And let's say there's a downward force at the end of 5,000 newtons. Let's say this is 0.6 meters and this is 0.4 meters. And let's say that these cables have an effective cross-sectional area of 0.01 meters squared. And a Young's modulus of 200 times 10 to the 9th pascals. First of all, what does that effective area thing mean? So cables are, it's not the same as a solid metal bar of that same thickness because it's strands of metal that are wrapped around each other. So a lot of that area inside the shape, like if you just measured the area by taking the radius of the cable, you'd be measuring a lot of air in there. And so the effective area is the area that's made out of metal. Okay, so you wouldn't get that by measuring the outer diameter exactly. And we want to know what are the tensions in the cables. All right, well, first thing we do is the statics, but you can see that this is going to be statically indeterminate because you could take either one of those two cables away and the thing would still be in static equilibrium until the cable broke, But so if you have a setup where you could take something away from the problem and the problem is still in static equilibrium, then clearly this is statically indeterminate. Statics isn't going to give us the answer to this. Okay, but let's do the statics first because that's going to give us at least one equation that's going to be useful in solving this. So free body diagram, and we're going to isolate the beam. There's an unknown force here, call that R, and then there's a tension here, T1, and a tension here, T2. And I didn't give a weight, so I guess we're ignoring that. And then there's a downward force of 5,000 newtons. then Newton's second law says Rx, Ry plus 0t1 plus 0t2 plus 0 negative 5,000 is equal to zeros. So Rx is equal to 0, we know that. And then Ry plus T1 plus T2 is equal to 5,000. Call that equation star. And now mathematically you can see that it's statically indeterminate. We've done everything. Well, that's not true. We haven't done everything yet. So let's go to the moment equation. About point, let's choose this left endpoint. There's no moment produced by R. The moment arm for that tension T1 is 0.6. And would that rotation be clockwise or counterclockwise? Counter, so it's positive. Same with T2, and the moment arm for that is 1. And then the moment arm for the 5,000 is also 1. And that one's going the other way, so that's going to be negative. And these add up to 0. So we have 0.6 T1 plus T2 is equal to 5,000. We can't solve either of these. So I'll call this equation star. This is 2 star. And how many variables do we have? 1, 2, 3. 2 equations. So it's statically indeterminate. We're going to have to figure out something, some restriction on the motion. Okay, so what's the restriction on the motion that we're looking for here? Look at this problem and see if you can think what we're going to use.
It's not going to go into the wall.
That's true, but we let's see, are we? It's not going to go into the wall. That's really close. So we're not going to. I guess we're going to assume that in a way. We're also going to assume that it doesn't go up or down the wall, and so yeah, our assumption is that this point of the rigid body stays exactly put, and that this is rigid, and so as these deform, we're going to get this thing, the endpoints of these two cables following a line. Like if you did a big deformation, it would be like this, you know what I mean? It's always going to make a line from this point and this point through the hinge. That was not clear wording at all, but you know what I'm talking about? Yeah. No. What it's going to be is that there has to be, so the deltas of these two cables have to make a triangle that goes, through that hinge. And so they can only deform in a certain ratio. Okay. So the constraint So if this is the initial position, the deformed position has to be this, where this is going to be delta 1, this is going to be delta 2. This is a right triangle. Now, if you really did a finite rotation of this bar, this would not be a right angle. Okay, because this, if it's rigid, this has the same length as this, right? And so this would be an isosceles triangle. This angle would be the same as this. But we're talking about, vanishingly small changes in angle. That's part of our expectation that deformations are small. And so we can approximate this as a right triangle, and it's going to make the math a lot easier. Okay, so what does this say? This is a right angle, and this is a right angle. This length is 0.6, and this length is 1. And so what we're requiring is that delta 1 over 6 is equal to delta 2 over 1. That's saying that, that angle is some theta. And for this little triangle here and this big triangle here, the tangent of that angle has to be the same. Those have to be similar triangles. Okay, so delta 1 has to be equal to 0.6 of delta 2. And now we're going to use the relationship between the tensions in the cable and the deformations. So delta 1 is equal to the tension in cable 1 times the length of cable 1, so whatever those lengths are. We're talking about the undeformed length of cable 1, so this is L. We don't have to know what that is. That's going to start out the same for both of them, and it's going to cancel out. Divided by EA. That's the same for both of them. And delta 2 is equal to T2 times L over EA. And so all of this together we can write as E1L over EA is equal to 0.6 T2L over EA. We can cancel a bunch of this stuff. And we see that T1 minus 0.6 T2 is equal to 0. And that's equation 3 star. Any questions about that? Okay, so now we have three equations for three unknowns. And the variables are T1, T2, and RY. So I'll just substitute 0.6 T2 in for T1. So I'll sub 3 star into 1 and 2. And equation 1 becomes, equation 1 star becomes RY plus 1.6 T2 is equal to 5,000. So this is, let me rewrite these as, so substitute 3 star into 1 star to 2 star. And equation 2 says 0.6 times 0.6 T2 plus T2 is equal to 5,000. So $1.36 T2 is equal to 5,000. So T2, what's 5,000 divided by 1.36? Say it again. 0.47 newtons. And then RY, what do you get for that? 882.35. And then T1 using equation 3 star. 2,205.88. Okay, so what we got is, because of the positions of these two cables, which one is closer to the end, which one is closer to the hinge, even though they're the same material and the same area, most of the force is going to be taken up by this cable at the end. Less is going to be taken up by that one. And that's because as this thing deforms in a straight line down like this one is always being forced to stretch more than this one. Okay, sort of an interesting problem. So yeah, so any problem like that where you have two members that are working together to counteract some external force, the location where you put these things is going to have an effect on how they support that load. Okay, let's see. Yeah, I guess that has to be true, right? Because those two tensions add up to more than 5,000. Okay. Any other questions about that one? All right, so now let's do the same idea, but for members undergoing torques. So now we're going to talk about angle of twist. And statically indeterminate bars and torsion. And what we're talking about is if you have a delicious piece of summer sausage and you apply a torque this way and a torque this way, before the deformation, you could draw a line across it like this with a marker. And after you apply that torque, that line is going to do this. That's exaggerated, but and this angle here, that's the Greek letter phi, and that's what's called the angle of twist. Everybody follow what I'm talking about here? Try to draw this straighter. Okay, so for this calculation, I want you to look at the form of the elongation of members in tension. So look at the basic form of delta for a member in tension. So we got, if we're just looking at the constant internal tension form, delta is equal to T times L over E times A. Okay, and let's think about what each of these multiples represent. So T is the internal load. L is the length. E is a material stiffness against the internal load. Let's say material stiffness resisting the internal load. And A is a geometric resistance to that internal load. Okay, so that's kind of a general way to think about each of these things. And if you think about those that way, it'll help you remember the form for the angle of twist for torque. So this angle of twist has the same form, same basic form. Phi is equal to, when we're talking about angle of twist, what's the internal load that matters? Torque. So fancy T. And then length is still length. Then we're talking about the material stiffness that resists shear stress. I'm going to call that G, and I'll give that to you in a second. But that G is just, just like E is the element of the stiffness matrix so you can go between stress and strain. G is the shear element of the stiffness matrix that lets you go from stress to strain. And then when you're talking about twisting, what's the geometric resistance to torque? You remember? When we were talking about shear stress due to torque. It wasn't it wasn't area. Area resists like a tension or a compression. It wasn't the area moment of inertia that resists bending. It's a third one. I sub P. Polar moment of inertia.
Oh yeah, of course.
If you go back, you can see that's all based on geometry, and it gives you a resistance based on the geometry to a torque. And then that G is equal to E over 2 times the quantity 1 plus nu. That's the shear element of the stiffness matrix. We've used the compliance matrix more than we've used the stiffness matrix. And if you remember, the compliance matrix has shear elements of 2 times the quantity 1 plus nu over E. Well, stiffness is the inverse of that, so you're just going to get the reciprocal. Okay, so just notice that there's that relationship between the macroscopic deformation in torque and the macroscopic deformation in tension compression. And then there's the two other forms too. So here are all 3 formulas for angle of twist. The first one says that the angle of twist is equal to the integral from 0 to L of the torque dx over GIP. Oh, you can also remember that because GIP is a funny thing to say. Yeah. Yeah. That's probably an easier way to remember it than the thing about. Yeah. Okay, so that's the definition. And then there's the one for piecewise constant internal torques. And that's just the sum from I equals 1 to N of T sub I L sub I over G I sub P. And I guess you could have geometric changes as you go along, so this could also be an I. You know, you could have something that has different diameter cylinders as you go across, a thicker part here and a thinner part here. And then the third one is for all these values being constant. That's the one that we just came up with. So phi is equal to internal torque times length over G I sub P. When do you use this one? Hopefully never. But when do you need that? Yeah, so if there's continuous changes of any kind. And then this one is for piecewise constant. And you have to use that form if it's piecewise constant for any one of these three that can vary piece by piece. We're not going to have anywhere the material changes from one part to another, although I guess you could. You know, you could have something that's like steel at one point and then wood at the other point, and then you would make that change there. I'm still not writing an I there, though. Am I? No. And then this one if everything's constant. Any questions about that? Great. So let's say that we have a bar connected rigidly to the wall and 700 Newton meter torque applied at the right end. And let's say that the G value is equal to 80 times 10 to the 9th pascals. And the polar moment of inertia is 1.57 times 10 to the minus 8 meters to the 4th. And we want to calculate the angle of twist along this whole thing. The first thing we have to do is calculate the internal torque. In this case, we have a reaction torque at the wall. I'll call that fancy T sub R. And then we have the external torque of 700 Newton meters. And the rotational equation about the x-axis says fancy T sub R is equal to negative 700 Newton meters. And then do a cut. This one cut is valid for every x. I give a length, 0.6 meters. So this is valid for every x between 0 and 0.6. So at the cut, the free body diagram looks like this. You have 700 Newton meters this way, and an internal torque T going that way. And so the X moment equation says negative 700 plus the internal torque is equal to 0. So that internal torque is equal to positive 700. You don't have to go through all that if you can just look at that and see that it's, you know, and if you can't now, you will by the time you do a few of these problems. But in more complicated problems, remember that you always can just go back to calculating the external loads, do the cuts, calculate the internal loads, and those internal loads are what we're looking for. Since this internal torque is uniform over the whole thing, our angle of twist is just going to use this formula, T times length over G I sub P. And so that's 700 times 0.6 divided by 80 times 10 to the 9. And then I sub P, 1.57 times 10 to the minus 8. And you get a total value of 0.334 radians. Okay, so how much is 0.334 radians? What kind of angle is that? How much is a radian about? There's 2 pi radians and 360 degrees, so each one is somewhere around 60 degrees, right? So this is about 20 degrees. So that's a pretty big angle of twist. And you know, that's not a super huge torque, but that's a bar that's almost a meter long. You know, it's what, this long. And so the longer this thing gets, the bigger that angle of twist could be. You could apply, if you had something that was 6 miles long and you applied a pretty small torque to the end, you could still get that thing to go all the way around multiple times and still never have very big strains. Okay. Yep. Mm-hmm. Yeah. I don't know, but so that's a good question. I don't really know what happens if you deform something in torsion until it breaks. I don't know what kind of shape it takes. But I do want to point out that we're still assuming that this is, so even though we're talking about twisting this thing 20 degrees, we're still assuming that this is in its linear elastic range. Okay, so if you had something that was 5 miles long and you torque the end of it, you'd get this thing to rotate a full time around or whatever. That's a huge deformation, it seems like, macroscopically. But each individual, like, local deformation is still really small because all of that deformation is happening over 5 miles. And so even though you have a big macroscopic deformation, you have really small strains. That means you have small stresses. And this is still totally in that linear range of, we're still not talking about permanent deformations. If you let go of it, it would happily go right back, you know. And you've seen that happen, or maybe you've seen that happen with like torsion springs. It's sort of the same idea. You know, a torsion spring is like, they used to use these in watches and clocks before electricity took all the fun out of timing stuff. But you have a hairspring that's, goes around and around and around, and this thing will oscillate back, and you have a you have this connected to. It's not really a mass, but you can think of it as a mass like that. This thing will oscillate over a big range, but that's not saying that any part of this spring is undergoing a big deformation. It's just every little part of this super long spring is deforming a tiny little bit. And if you integrate it over the whole length, it comes out to be a big deformation. But it still stays in its linear range. It still obeys Hooke's law like any spring does. So, any other questions about that? Yes. Yes. The thickness of the bar goes into I sub p. And what's the formula for I sub p for a round? We only did it for a round cross section, but I sub p is equal to, I think, pi over 2 times the radius to the fourth. I think that's what the formula was. Yeah. And so, yeah, your intuition says if this thing was, so if this bar, this 0.6 meter long bar was, and let's say it's steel or copper, it's some kind of metal. If its cross section looked like that, and you applied this fairly small torque to it, even though 0.6 meters is pretty long, you wouldn't get any twist at all, basically. And the way that would happen is you'd get a much bigger value of that polar moment of inertia. And so then in this formula, you'd be dividing by something big, and you'd end up with a much smaller value of the angular twist. Any other questions? Okay, so to use this in a statically indeterminate system, so let's say that we have a wall here and a wall here, and those are fixed, those aren't going to move. And we have a bar in between them with fixed joints at both ends. And let's say that somewhere in here, we apply an external torque of 1,000 Newton meters. So let's say that this is 3 meters. This is 1 meter. And let's say that Young's modulus is 200 times 10 to the 9th. That's steel. Poisson's ratio now we need, and let's say that that's 0.25. And let's say that this has a circular cross section of 1 centimeter. What are the external loads? Okay, so this is going to be statically indeterminate because we're going to have one useful equation from Newton's laws. That's going to be the x moment equation. Okay. So that's one equation, but we're going to have a torque here and a torque here. So two variables, one equation. Those two torques together have to counteract this. Okay, so probably we're going to get each of them applying a torque in the opposite direction, and those have to add up to 1,000. Intuitively, do you have a sense of which of these two torques is going to have a bigger absolute value? Yeah, this one's going to have a bigger absolute value because it's closer to the load. And so we're going to first use statics to get that first equation that's going to tell us this plus this is equal and opposite to this. And then we're going to do our cuts, figure out the internal torque on this section and the internal torque on this section. Then we're going to calculate the angle of twist based on these variable values for internal torques. And then we're going to say, well, what's the total angle of twist as you go from here to here? It has to be 0. It can be something in between. You know, like if you drew a point with marker here and then applied the torque, that point with the marker on it would move. But here, that's fixed to the wall. Here, it's fixed to the wall. So the total angle of twist is going to have to be 0. Okay, so that's the idea. I'll do this problem next time. And like I said, bring questions related to the test, and I'll answer those first.